Hello everyone, I hope you're all doing very well and I hope you're all ready to do some more chemistry. Today we're going to have a look at our third homologous series called the cycloalkanes. Now the cycloalkanes are different in structure from the alkanes and the alkenes, and as the picture might suggest, the difference in structure is because the cycloalkanes are all circular or ringed structures. Their carbons aren't in a straight line, they're all connected in a ring. And we'll have a look at that and show you exactly what we mean by that in just a second. But just to appreciate that is what that kind of start of the word cyclo means. These cycloalkanes are in a kind of circle, in a ring structure. And today's learning intention is to do exactly that, is to explore the cycloalkanes as a homologous series. And what we'll be looking at in the video, well, we'll be looking at describing and drawing and naming the cycloalkanes and appreciating that they're part of a homologous series, so they have their own general formula, and we'll talk about some uses of these cycloalkanes as well. Now the cycloalkane family, as I said, they all have these circular or ring type structures, are not in a straight chain. Since they've got this kind of last name, the second name ending in A and E, it tells us a lot about the molecules as well. It tells us that they wouldn't have a double bond, that they would be saturated, but we'll come on to talk about that more later on. They're a family, just like the alkanes and the alkenes. They're a homologous series, a group of compounds with the same general formula and similar chemical properties. And of course, since they all belong to homologous series, they look quite similar as well. What are the headlines then with cycloalkanes? Well, they're the third homologous series that we've come across. They have ringed or circular structures. That's what the start of the word means. That cyclo part tells us that we have a ringed structure. And then if we look at the last three letters, we're looking at A, N, E, which tells us that they're saturated and they only contain single bonds. They're not like the alkenes ending in E, N, E, which tells us they've got a double bond. No, the cycloalkanes are saturated and only have single bonds. Right, let's have a little look at drawing a couple of these cycloalkanes. Let's start with cyclopropane and figure out how this would look and how we would go about drawing it. Well, we look at the first part of the word here, and it tells us, well, it's got a cyclo part. We know that it's going to have a ringed structure. All these carbons are going to have to be joined in a ring. We need to know how many carbons we're working with, and that's what the prop means. So we look at that prop, and as we know, that is the prefix for 3 carbons. And then the last part of the name as well gives us some information. It tells us that we have a saturated molecule, something that only contains single bonds. So that's how we're kind of using our scientific literacy skills here to break down the word and to figure out how to draw this. So let's have a little go. We know we've got 3 carbons, so I'm going to draw it almost like a kind of triangle with these carbons. Since it's a cycloalkane, these carbons are going to have to be joined together in a circle or in some sort of ringed fashion. And there we go, I've got my carbons all joined together. And now we kind of fill in the rest of the rules. We know there's only going to be single bonds, so I'm not going to be putting any double bonds in. That'd be wrong. And as we know, each carbon makes 4 bonds. So this one has 1, 2. Let's put in another 2 onto this carbon, and then add in the hydrogens as well. This one's only got 2 bonds already, so there's 3 and 4. Make sure every carbon gets 4 bonds. And there we have it. That is cyclopropane. See how it's different from just ordinary plain old propane, where we have all our carbons, 3 carbons, that's what the prop means, and our hydrogens. Propane is just in a straight line, whereas cyclopropane, we've connected, we've bent round the carbons and we've joined them together into this ring-like structure. Let's look at a second example now. Let's look at cyclobutane. and do the exact same thing. Break down the word, figure out how we're going to draw this. Cyclo tells us that it must be in a ring. Bute, well, that means that we have 4 carbons, and ane, as we know, is telling us we've only got single bonds. There's no carbon to carbon double bond there. So our 4 carbons, let's draw them out and try and put them into some sort of ring-like structure. I'm going to draw it as almost like a square here, connecting up my carbons. And there we go. We've got our 4 carbons in a ring. They're all connected together. It's not a straight chain because we've got a cycloalkane. And then do exactly what we always do. Count up the number of bonds on each carbon, and they have to add up to 4. Putting in the hydrogens as well, and there we have it. There's our cyclobutane molecule. And we could even look at a third one here, because if we look at a third one, we might be able to figure out the general formula as well for the cycloalkane. So let's look at cyclopentane. Pent tells me I've got 5 carbons. Now this is when it kind of gets tricky to put these in some sort of ring. As long as you're joining your carbons in a ring, it doesn't really matter what shape you put them in. I'm kind of drawing it like a little house almost here, just because that seems the easiest way for me to do it. I've got my 1, 2, 3, 4, 5 carbons. That's what pent means. They're in a circle, perfect, or a ring, and they've only got single bonds. That's what ANE means. And then we'll go ahead and fill in our hydrogens, making sure that, I'm just going to change that just to make it look a little bit neater, making sure that every carbon has its 4 bonds. This one's already got 2, so it needs another 2 bonds put in. Same with this one, already got 2, let's put in another 2. And there we have it, there's our cyclopentane molecule. Okay, let's see if we can figure out the general formula now for the cycloalkanes. Remember, these are homologous series, so they have to share the same general formula and they'll have similar chemical properties. Let's get the molecular formula for each of these. So cyclopropane, we've got 3 carbons, so it's going to be C3. How many hydrogens do I have? 1, 2, 3, 4, 5, 6. So C3H6. Go on to cyclobutane. Get the molecular formula. 4 carbons, C4, and hydrogens 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. Now it's worth pointing out here as well, this is quite sloppy. If you look at this hydrogen up here, that's no good. Make sure that your drawings are as neat as possible. Mine are not very good right now, so make sure that the H's look like H's and not anything else. Look at this one, that's rubbish. You will do much better than I will. And let's look at the last one here. We've got 5 carbons, C5 and H, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. C5, H10. So we've got our 1, 2, 3 molecular formulas for our cyclopropane, butane and cyclopentane. Now that should allow us to work out our general formula for our cycloalkanes. Won't take a genius, a mathematical wizard, to work out that when we've got 3 carbons, I've got double that number here, and 6 hydrogens. If I've got 4 carbons here, I've got double that number, and 8 hydrogens, and the same for the last one as well. So our general formula for the cycloalkanes is CnH2n. Now if you remember to last video, that is the exact same general formula as the alkenes. So this general formula CnH2n applies to both our alkenes that we looked at last time, and it applies to our new and third homologous series that we've just looked at now, our cycloalkanes. And just to quickly recap what we've talked about, the cycloalkanes, the names all end in ANE, telling us they only have single bonds. They begin with the word, or the prefix rather, cyclo, telling us that they are circular structures, ring structures, and as usual, They are very useful materials, very useful substances that can be used in fuels and solvents and all sorts of other uses as well. The general formula is the exact same as the alkenes from last video. It is CnH2n. And here we've got cyclopropane that I drew for you earlier, just a kind of another representation of it in the kind of model form. And as we've seen before, it's in a ring structure, and the molecular formula C3H6, well, that fits in with the general formula CnH2n. Little table here for us to fill out. Again, you can pause the video and do this in a little bit of paper or however you want to do it, but it's worth your time just sitting down and trying to figure out what the molecular formula would be, what the structural formula would be, and then if you're feeling confident as well, you can go into the shortened structural formula. So I'll give you a chance to pause the video and have a little go at that now. Right then guys, let's look at filling out this table here then. So the first one, cyclohexane. Well, we know that it's a cycloalkane, and so it must have the general formula CnH2n. We look at the name, we look for the prefix hex. That tells us that we have 6 carbons. So it's C6, and then to get the number of hydrogens, we just times that 6 by 2 because H is 2n. So we are 6 times 2 is 12. So cyclohexane C6H12. We could look at the full structural formula as well just to confirm that. We've got 1, 2, 3, 4, 5, 6 carbons, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens. So it takes a little bit longer to do it that way. Better off using the general formula to figure it out. Here we've got our structural formula. Now, our shortened structural formula, I should say. Now, as I said when we went through this in the last couple of videos, we don't really want to put in any bonds that we don't have to. We normally don't put in any single bonds. However, this is still a structure. Even though it's a shortened structure, it's still a structure. And we have to convey the fact that these cycloalkanes and these cyclical structures have a ring structure. The carbons are not in a straight line, they're in a ring. So we put in those single bonds which are used to produce that ring there. The other single bonds to the hydrogens, we won't bother putting those in, and that's how you would do your shortened structural formula for a cycloalkane. Let's have a little go at practicing the full structure and then the shortened structural formula for the next one. Cycloheptane, hept is the prefix for 7. Use the general formula, and we know that we've got 14 hydrogens as well. Let's have a wee go at drawing this out. Now, this is where it gets a little bit tricky to kind of figure out where you're going to put all your carbons. It's nice if you can get them all in a nice kind of symmetrical ring like this, but when you've got an odd number, it gets a little bit trickier. So as long as our carbons are all joined together, it shouldn't really matter too much in terms of style. You're not going to get any extra style points for drawing it in any kind of particular way. So there we go. I think I've got all our 7 carbons in a ring there. Yeah, I've got a longer bond here compared to the rest of them, but that's fine. We're allowed to do that. Let's just check. 1, 2, 3, 4, 5, 6, 7. Great. Now I know I need to put in my 14 hydrogens, and well, each carbon makes 4 bonds, and every carbon here already has 2 bonds, so every carbon will get an extra 2 bonds with hydrogens on the end of them. And we'll just go through and complete I'll put this hydrogen in there, complete the structure like this. Now I'm just a wee bit pushed for space in this box, and that's fine, but as long as we're following all the correct rules, as long as we're making it as clear as possible that the bonds are going to the correct atom, we should be fine. We'd ideally want to draw this a little bit neater, but we'll just push for space right now. Now we can look at drawing the shortened structural formula. Again, like I said before, We don't want to put in all of these single bonds to the hydrogens, but we still want to show and convey the structure of the ring. So let's put in the carbons as we had them, like this, and then we can put in the hydrogens as well, just next to each carbon, H2, group them together. We do not need to draw these bonds in because we're drawing our shortened structure this time. And there we go. Right, cyclooctane then. Oct is 8, so it's C8, and then we times that 8 by 2 to get the number of hydrogens, which is 16. And again, we can go through and do our shortened structural formula this time for our cyclooctane molecule. Getting a wee bit tricky, but that's not too bad. Putting all our carbons in the ring, showing that we've got this cyclic molecule, and then we don't need to bother with any of the other bonds, just putting in the H's at the correct position next to the correct carbon, like that. And there's our shortened structural formula. And all I've done there is I've just looked at this full structure and I've said, well, let's take this first carbon here, let's say this is carbon number 1. What has it got bonded to it? Well, it's got 2 hydrogens, so I'll put H2 next to that carbon. Then I go on to the next carbon. Well, what's this got bonded onto it? And they're all the same. Every single one has 2 H's on it, so I'll just pop those next to those carbons there. And then just to end the video, just to kind of recap what we talked about last day as well. As I've said throughout, these cycloalkanes ending in ANE are saturated molecules. They contain only single carbon-to-carbon double bonds. There's no double carbon-to-carbon double bonds, there's only single ones. If you remember from last time, we said that there's a chemical test to see if a molecule has a carbon-to-carbon double bond, and we could use bromine water or bromine solution. And here, if we look at the bottom of the image, we've got a picture here where it's showing us that colour change. If you've got an alkene ending in ENE with a carbon-to-carbon double bond, that will decolorize or turn the bromine water from brown to colourless. That's because the double bond changes its colour. Whereas if we've got an alkane or a cycloalkane, like we've been talking about, where there's no double bonds, well, the bromine water would stay brown, it would not decolorize, and that's how we could test between an alkane, a cycloalkane, or an alkene to see if it's got a double bond. Okay guys, thanks for tuning in, and I hope you're all doing really well, and that's the end of the video.